Good day and welcome back to part one of our discussion on double integrals over general regions. In this video we will begin our discussion which builds upon our previous discussions where we evaluated and interpreted double integrals over a rectangular region. And just as a quick reminder, remember when we're integrating over a rectangle AB cross CD, the first interval is giving us an idea of where the x values lie, the second interval the y values. And the double integral of a function of two variables over this rectangle is interpreted geometrically as a net difference of volumes. So we'll say the net difference of the volume enclosed between the graph of the function, so that would be the surface z equals f of xy, and the z equals 0 plane, all on or above that rectangular region R. In this first video investigating double integrals over general regions, I really just want to point out the limitation of thinking about only integrating over rectangles, especially when we're trying to calculate something like an enclosed volume. And a typical question we are going to encounter over and over again throughout this entire chapter is to find the volume of a solid that we described for you. In this example, we are asked to find the volume of the solid, bound it in the first octant by the plane 3x plus 2y plus z equals 6. And something I will strongly encourage you to do as you practice problems, and in a sense require you to do on graded problems, is to sketch a picture of this solid whose volume we are finding. And the reason we do this is to help set up the integrals and also to get geometric intuition. When it comes to this plane of interest, 3x plus 2y plus z equals 6, the simplest way to picture it in the first octant is to, once again, similar to previous examples, think about those positive intercepts. That is, what is the x-intercept, what is the y-intercept, and what is the z-intercept. And we do this almost purely by inspection. We think if y and z happen to be 0, x must be 2. If x and z happen to be 0, y must be 3. And if x and y are both 0, then z is going to equal to 6. And it's also important to remember that our pictures do not need to be perfect. They need to just get the general idea across. So roughly speaking, we have our x-intercept sitting at 2, 0, 0. Our y-intercept sitting at 0, 3, 0, and our z-intercept sitting at 0, 0, 6. And we are looking for the plane going through those 3 points. So roughly speaking, we can represent that by just drawing this triangle, and then the portion in the first octant would be everything inside of that triangle. Now, if we're going to think about finding the volume of this, what we need to do is go back to our interpretation that a double integral is giving us a net difference of some enclosed volume. And in this case, I'm going to shade this region in the xy plane and note that the volume would be the double integral over that region D, and what we need to integrate is the surface given by our function of two variables. That is, we need to put it in this form z equals. And if we look above, that associated graph would be z equals f of xy. And if we isolate the z, we have 6 minus 3x minus 2y. And the volume will be the double integral over d of our surface. That is, how much volume is enclosed in the first octant below that plane. And the reason I'm starting with this example is that it's something easy enough for us to accurately sketch a picture, but it also very clearly illustrates the limitations of only dealing with rectangles. If we focus in on this region D, and we sketch it in a separate xy plane, we have a triangular region which goes 2 units in the x direction, 3 units in the y direction, and looks like this. And the observation that we need to make is, how do we go from that region D to setting up the limits of integration for our double integral? So the big question is, how do we set this up? And it turns out that's the major topic of this new section. This would be considered a general region, which is really anything that is not rectangular. And let me finish this video up by investigating or stating a few properties that may look familiar from our past experience dealing with, say, just single integrals. If we have some region of integration D that we would like to work with, and note I've purposely drawn this so that it's not a rectangular region, it is possible for us to break this up into pieces, much like we would break a single integral up into two littler intervals. And we can rewrite this as the integral over d1 of a function plus the double integral over the region d2. So we're just kind of, in a sense, splitting up how we are determining this enclosed or net difference of volumes. Let me also remind you of a property that we mentioned in a previous video. If we were to evaluate the double integral over a region D of the function 1, let's think about what that would give us back. So in general, we might have some region D that's not rectangular, kind of one of these general regions. And when we integrate the function 1, we're thinking how much volume is enclosed between the surface given by z equals 1 and the z equals 0 plane, but sitting specifically above that D. So the solid whose volume we are hoping to calculate would really just be that region extended 1 unit up in the z direction. And the volume of this would be its height, 1, multiplied by the area of its base. So the value of this double integral, the enclosed volume, is simply the area of the region D, which is a property we will occasionally make use of. That finishes my introduction into double integrals over general regions, but what remains is the process that we are going to use to set up our limits of integration so that we can, in fact, evaluate one of these double integrals. And for the note packet in this section, pages 2 and 3 specifically, will be discussed in the next video. If we were meeting face-to-face in class, I would give you those 2 pages and have you spend roughly 20 to 30 minutes working with your neighbors, discussing these problems as I walked around and interacted. So what I would strongly encourage you to do is to take a look at those 2 pages and go through as much of them as you can and try to develop that understanding. And then in the next video, we'll kind of start from the top and go through that information. So stay tuned and take care.